In this video, we will talk about what the chain rule is. So I want to motivate this with a question. So let's say that y is equal to the function x cubed minus 4x plus 1 over x to the 10th power. And the question is, what is the derivative of y? What is dy dx? That was one of our notations for how we write the derivative of this function of y. Okay. So let's first just pause for about 30 seconds, and think about, based off of what we know now, how would we do this derivative? So 4, 3, 2, 1, pause the video. So this is a mini pause, 30 seconds. Think about how we would do this using our current methods. So with our current methods, okay, so one more time, pause the video, think about this for 30 seconds if you haven't done so yet. Alright, so hopefully you've done that. Hopefully you've paused the video for about 30 seconds to think about this. It's really important to use that time to reflect on what we've seen before and how we would use that to tackle a problem like this. Okay, so let's talk about it. With our current methods, we would expand x to the third minus 4x plus 1 over x to the 10th power. So that means when I have this thing to the 10th power, that means multiply it by itself 10 times. So this whole thing, x cubed minus 4x plus 1 over x, times itself, times itself, times itself 10 times, we'd have to multiply that whole thing out. And then, and only then, would we be able to take the derivative. So the verb for that is we say then differentiate. That just means take the derivative. But hopefully we can see at this point that that's very tedious. That is going to be super, super tedious to do. It's doable, but it would take a really long time. Okay, so I'm going to put a sad face here. Okay, so that method, doable, it would just take a really long time. It would be nice if there was a better, quicker way to do this. So we need a new rule to differentiate stuff that looks like this. So the general form for a function that looks like this is, if I have a function, f, and then inside of it there's another function that I'll call u of x. So when we have something like this, when we have a function inside another function, this is called a composition of functions. So a composition of functions. Okay, so that's probably a term you would have seen maybe back in algebra. A composition of functions just means we have a function inside of another function. Okay, so the rule to take the derivative of something like this, a composition of functions, is called the chain rule. Alright, so now let's state what the rule is. So it says that if f and u are both differentiable functions, then d dx, so that means if we're taking the derivative of this function with respect to the variable x, so the derivative of f of u of x is equal to f prime of u of x. So we take the derivative of the outside function, that gives us f prime, but we keep plugging in the same inside function, u of x, into it. And then we multiply that by the derivative of the inside. So we multiply it by u prime of x. Alright, so let me also state a memory trick for this. So the memory trick for this is to remember that if we take the derivative of f of x, so this is a simple function, well, our notation for that is, we write this as f prime of x. That was just one of our notations for the derivative. What we're doing with the chain rule is we're taking the derivative of some outside function f. And then within it, there isn't just x anymore. There's some stuff. There's some more complicated stuff inside of that outside function f. And the chain rule says that when we do the derivative of this f of stuff, this composition of functions, this chain of functions one inside of another, that's why it's called a chain rule, we take the derivative of the outside, f prime, and then you keep the stuff, the inside stuff, the same. So that's matching up with f prime of u of x. And then you multiply by the derivative of the inside. You multiply by the derivative of the stuff. Okay, so this is a little memory trick for the chain rule. Okay, so I also just want to state the chain rule in our other notation that we had for derivatives. So this is that Leibniz notation. This is when we write stuff like dy dx. That's Leibniz notation. The other notation is this prime notation for derivatives. So I also just want to write the chain rule in Leibniz notation. This is something that we'd see more in Math 31 in the next math course after this one. Okay, so in Leibniz notation, if our function is y of u of x, then if we want to take the derivative of y with respect to x, what that equals is, it equals dy du, so the derivative of the outside function with respect to the variable u, times du dx. And that means the derivative of the inside function with respect to x. And the way sort of, the memory trick to sort of remember this is that on the right-hand side, the du terms sort of like cancel. So the du at the top of the dx term and the du in the denominator of the du dy, the dy du, they sort of cancel. And when we sort of cancel them, we're just left with dy dx. So of course, they don't literally cancel because these things aren't literally fractions. Dy du is not an actual fraction. It's just a notation for a derivative. Same thing with du dx. It's not an actual fraction. We just notate the derivative in this way. But nonetheless, that's a good memory trick for remembering this form. That the du sort of cancel, not actually, but we can visualize it in that way. And we're left with the dy dx, which is the same thing that we have on the left-hand side. All right, so let's look at an example. All right, so let's actually do the derivative of this function that we began this video by looking at. Okay, so this function is a composition of functions. It has the form f of u of x. There's some outside function here, there's some inside function here. So let's see if we can recognize what those are, what that outside function f of x is, and what the inside function g of x is. Okay, so this is a bit of review back from algebra. So pause the video for about 45 seconds, maybe a minute, and see if you can determine what that outside function is and what the inside function is. So 4, 3, 2, 1, pause the video. Pause this video for about 45 seconds and see if you can determine those two things, outside and inside function here. Alright, so hopefully you did that. Hopefully you paused it for about 45 seconds. So now let's talk about it together. So looking at this whole thing, I see that within the parentheses, x cubed minus 4x plus 1 over x has been sort of plugged into the parentheses. So x cubed minus 4x plus 1 over x is actually our inside function. But what is that whole thing in the parentheses being plugged into? It's being plugged into sort of this 10th power. That means the outside function is actually x to the 10. Because if you take what's inside, if you take the g of x, and you plug that whole thing, whoops, I wrote g of x, but I meant to write u of x. Okay, let me erase that. Sorry, u of x there for the inside function. Okay, so if we take that u of x, so what u of x is, and now if I plug it into that outside function, plug it in where the x is, that gives me the function that we're looking at, x cubed minus 4x plus 1 over x to the 10th power. Okay, so let's remind ourselves what the chain rule says the derivative of this composition should look like. So dy dx, our derivative, should look like f prime of u of x. So the derivative of the outside first, but keep plugging the same inside thing in, times the derivative of the inside function. So times u prime of x. All right, so I really want to break down and describe what these things are saying. Okay, so for this first part, the chain rule says take the derivative of the outside, but when we do that, keep the inside the same. So that's a phrase that you're going to hear me say a lot in these videos as we do these chain rule problems. As we start to do them, I'm going to be saying stuff like, okay, now we first take the derivative of the outside function, but when we do that, keep the inside the same. And that means we keep plugging in u of x into that. Okay. All right, so for the second part, for this whole second part, now what we do is we multiply this by the derivative of the inside. Okay, so let's see if we can do that for this example. Let's see if we can now put this formula into action. So if we do that, and we start to write down dy dx. So first I have to deal with the outside function. And the outside function it's the fact that we have this power here. The power is what's sort of contributing to the outside function, being x to the 10. So the way we deal with the derivative of x to the 10 is we do the power rule. So in this case, the power is going to come down. The power is going to come down. And then my new power is going to be a 9. But instead of writing an x inside the parentheses, the chain rule says, well, when you take the derivative of the outside function, so when you take the derivative of the outside, keep the inside the same. I have to keep plugging in the same inside function in after I take the derivative of the outside part. So I'm going to keep writing x cubed minus 4x plus 1 over x inside here. Okay, so that right there is my f prime of u of x. It's the derivative of the outside, but after we take the derivative of the outside, we are plugging in the same inside function into it. Okay, but that gets multiplied by the derivative of the inside. So I have to multiply by the derivative of the inside. So the inside was x cubed minus 4x. And then to take the derivative of 1 over x, it's going to be helpful to write it as x to the negative 1. Okay, so this right here represents u prime of x, the derivative of the inside. So now let's just evaluate that derivative. Okay, so evaluating this, we end up getting, so dy dx. So the first part stays the same, 10 times x cubed minus 4x plus 1 over x to the 9, and then times that second, times the derivative of the inside. Derivative of x cubed is 3x squared. The derivative of minus 4x is minus 4. So this is just all power rule here. And the derivative of x to the negative 1 is minus, the minus 1 comes in front. And then I get x to the negative 2 when I subtract 1 from the power. Okay. And at this point, we have finished taking the derivative. So this is our derivative using the chain rule. All right, so I want to end this example by just talking about this in the context of our memory trick. So in the context, I'm going to zoom it out a little bit. So remember that when we take the derivative of just the outside function on its own, in this case it's x to the 10, and I use the power rule, we get 10x to the 9. But in this case, we're not taking the derivative of x to the 10. We're taking the derivative of some stuff to the 10th power. And the chain rule says, okay, well, if you got some different stuff inside of whatever the outside function was, then use the chain rule. And the chain rule is going to say, okay, handle the outside part first. And that's the fact that we have something to the 10 power, x to the 10 power. Bring that power down, and then subtract 1 from the power. The chain rule says when you take that derivative of the outside part, keep the inside the same. So keep the inside as the stuff. And then multiply this by the derivative of the stuff. That's the derivative of the inside. Okay, so that's just what this looks like in the context of our memory trick. So let's look at another example. Let's do another example. So in this next example, we have this function a of x, which equals e to the negative x cubed over 2 plus the cube root of ln of x. And I want to find the derivative. Okay, so in this problem, there are sort of two parts of this that are being added, two terms that are being added. So we're going to have to take the derivative of both of these. So with this first term, this fraction, it might be tempting to look at this and think, fraction, does that mean quotient rule when I take the derivative? And I could use the quotient rule if I wanted to, but there's a way to get around it and not have to use it here. And that's because when you have a constant, like 2 in the denominator, we can move that constant in front and get 1/2 times e to the negative x cubed. And now I just have the function e to the negative x cubed with a constant in front of it. And once it's in this form, we don't need the quotient rule anymore. Okay, so that's a tip. If you have a fraction for your function, and if either the denominator or the numerator of your fraction is a constant, we can typically just move that constant to the front, and then what's left over, in this case was e to the negative x cubed, is typically going to have the form where I don't need the quotient rule anymore. Okay, so that's helpful to keep in mind. So let's begin the process of taking this derivative. So if we want to take the derivative of this, we need to take the derivative, so d dx, of 1/2 e to the negative x cubed, and we're going to have to add that to the derivative of the next part. So to take the derivative of this cube root of ln of x, it's going to be helpful to rewrite that cube root as a 1/3 power. So we're taking the derivative of ln of x to the 1/3 power. Okay, so in doing these two derivatives, for the first one, we have something of the form e to the stuff. We have this e, but in the exponent, we don't have just x. We have something more complicated. We have e to the stuff. And that's actually a composition of functions. This has the form f of u of x. It's actually a composition with what's the outside and what's the inside. So the outside function, the f of x, and then I'll also write u of x. So the outside function is actually just the e to the x. And when I write that down, you might be wondering, wait, I don't see e to the x here. I see e to the stuff. And that's because something has already been plugged into the outside function. We've already plugged something in for the x. What's been plugged in is stuff, is the stuff. That's what the inside function is. If you take stuff and you plug it in, if you take the stuff and you plug it into the outside function, where the x is, instead of getting e to the x, we'll get e to the stuff. Okay, so the memory trick here is, if we take the derivative of e to the stuff, so if we take the derivative of e to the stuff, the chain rule says, well, first handle the derivative of the outside part. And the derivative of the outside part is just derivative of e to the x, which is e to the x, but the chain rule says, when you do the derivative of the outside, keep plugging the same stuff into it. So instead of writing e to the x, we'll write e to the stuff, and then we multiply by the derivative of the inside part, and that was the stuff. So the takeaway is that when we do the chain rule, I'm going to put this all in a bubble, on e to the stuff, when we take the derivative of e to the stuff, we get e to the stuff times the derivative of the stuff. Okay, so if we do that on this 1/2 e to the negative x cubed, the 1/2 is a constant, so I can keep that out in front. And then doing that for the e to the negative x cubed portion, we will get e to the negative x cubed, that's e to the stuff, times the derivative of that stuff, times the derivative of negative x cubed, because that's the derivative of the inside. All right, so that's the first part. Now I still need to take the derivative of ln of x to the 1/3 power. And that's also going to require a chain rule. The outside part for this function is the fact that I have this 1/3 power. So first I need to deal with that 1/3 power. So the 1/3 is going to come down in front. And then I'm going to subtract 1 from the power. That'll give me a negative 2/3 for the exponent. So far that's the derivative of the outside part. The outside part is the fact that I have something to a power, x to the 1/3 power. But when we do that, the chain rule says, well, keep plugging the same inside thing in. So keep plugging in ln of x. Okay, so that's the first part of it. The next part of chain rule says, well, now multiply this by the derivative of the inside. So the derivative of ln of x. Okay, so let me give myself a little bit more room. Let's continue writing this. Ooh, kind of shifted over there a little bit. Let's continue writing this down here. All right, so we have 1/2 e to the negative x cubed times the derivative of negative x to the 3rd, which is negative 3x squared. And then we have plus 1/3 times ln of x to the negative 2/3. And I have to multiply by the derivative of ln of x, which we know is 1/x. And at that point, now we've completed all of the derivatives. This problem actually involved the chain rule twice. I needed the chain rule for this term. We needed chain rule here. But we also needed chain rule for the next term. All right, so let's go ahead and box this. So this is our answer right here. So when a question like this asks us to take the derivative, it's fine to leave the answer in this form once we've finished taking every derivative that sort of showed up in it and not simplify it further. Okay, so let's do another example. I mentioned in the overview video that the chain rule is a rule that's where it's so important to do practice problems. All right, so I also just scooted that up to give myself a little bit more room. But we're really going to focus on doing a lot of examples, a lot of practice problems to get more comfortable with the chain rule. But remember, as with all concepts in our class, it's not enough just to watch me do examples in the videos to master something. It's really important that you practice doing questions like these on the homework and, if necessary, doing extra practice problems in the worksheet to really master this stuff. And when you have questions, that's totally normal. Some of this stuff is challenging. It's tricky to pick up. So when you have questions, definitely reach out and ask them. I'm happy to help, and feel free to also use our other resources to reach out and ask those questions. Because ultimately, I want you to understand how to do this and how to master this content. All right, so let's talk about this problem right here. Okay, so let me begin with sort of the memory trick for something like this. So in this problem, I see something of the form ln of stuff. And that's a function inside of another function. This has the form f of u of x, with the outside function f of x being equal to the ln of x technically. But we might be wondering, wait, I don't see ln of x here. I see ln of something different. But that's because we've already plugged something in for u of x. We've plugged something in inside where the x used to be. We've plugged in the stuff. So the outside function with ln of stuff is ln of x. The inside function is the stuff. Okay. So remember, the derivative of ln of x is 1/x. But when we do the derivative of ln of stuff, The chain rule says we'll take the derivative of the outside part first. The ln, that derivative is typically 1 over x. But instead of writing 1 over x, the chain rule says keep plugging the same inside thing in. So keep writing the stuff there, because that's what's inside. All right, so that's the derivative of the outside, but I'm still plugging the same inside thing into it. But then we multiply that by the derivative of the inside. We multiply by the derivative of the stuff. So that's the memory trick for what the derivative of ln of stuff looks like. The derivative of ln of stuff is equal to 1 over the stuff times the derivative of that stuff. And this comes from the chain rule. All right, so let's use this to take the derivative in our example. So f prime of t here is going to be, so my outside function is the ln. So I do 1 over the stuff inside, 1 over t minus square root of t to the 4th plus 10. Ooh, 10. And then multiply that by the derivative of the inside. So multiply by the derivative of t minus, and then to take the derivative of this square root term, it's going to be helpful to write it as a power. So 1/2 power, and what's inside of it is t to the 4th plus 10. Okay, so what's left for us to do, let me just write that 10 better. What's left for us to do is figure out the derivative of t minus t to the 4th plus 10 being raised to the 1/2 power. So the derivative of t, well, that one's going to be easy. But the derivative of this whole thing to the 1/2, this actually uses the chain rule again. We actually need the chain rule again to take the derivative of that portion. Okay, so let's do this. So we have f prime of t equals 1 over, and we have t minus the square root of t to the 4th plus 10. So the stuff at the front, that just stays the same. Okay, but now I have to multiply this by the derivative of everything in this parentheses. The derivative of t is 1. That one's not too bad. And now for this whole thing to the 1/2 power, we need chain rule. First, we deal with the outside portion. The outside portion is actually the fact that I have t to the 1/2 technically. I have to deal with that power, because the power is the outside portion. So the power rule says bring that power down, and then subtract 1 from the power. So I'll get negative 1/2 as the power. And when we do that, we keep plugging the same inside function in. So we keep plugging in t to the 4th plus 10. So far that's the derivative of the outside, but keeping the inside thing the same. And now we multiply that by the derivative of the inside. So the derivative of, actually I might need to go to the next line to write this. Derivative of t to the 4th plus 10, because that was what was inside. And now I close this parentheses. Okay, so we're getting there. One more derivative to do now. Okay, so let me just move some of this stuff over. Okay, so let's write up our derivative now. So f prime of t equals, the beginning part stays the same, 1 over t minus the square root of t to the 4th plus 10 times, and then we have 1 minus 1/2 times t to the 4th plus 10 to the negative 1/2. And now we have to multiply by the derivative of t to the 4th plus 10, which is 4t cubed. And at that point, we've finished this. This problem involved the chain rule within the chain rule. And that is our derivative. Okay, so we've slowly ramped up the difficulty level in these examples, but doing these examples is really important to get comfortable with the chain rule. But remember, it's super important to get that practice on your own. So in terms of our goals for this section, we have introduced what the chain rule is, to deal with derivatives of compositions of functions, and we've talked about recognizing how and when to apply it. In the next video, we are going to do even more chain rule examples.